Gabby. Take your time. Thank you.
Okay, better. Good. Okay, so then this is the last lecture on dark matter. Well, I try to put the things that we talked about before together to arrive to current state of the art. Right, so first I'll tell you a bit about gamma ray sky. So what are the background for dark matter searches? So this is something that Franz and others already talked about, but I'll again try to, put it together for in the context of dark matter search. So as Franz was saying, so how does the gamma ray sky looks like? So we see that the main features. So we see that in terms of this extended emission along the galactic plane, I will tell you more about this later. This so-called interstellar emission or diffuse emission shines very brightly, at in Fermi energy range up to hundreds of GeV or so. But then when you get to TeV energies, where you observe the sky with Cherenkov telescopes, then one, this emission gets much fainter, and two, it's very hard to observe this emission because if you remember, we were talking about the experimental technique of Cherenkov telescopes, is that first they have rather limited field of view, and then there is lots of cosmic ray background. And so if you have some emission in small field of view, if you have some emission that is almost isotropic, like your cosmic ray background, it's very hard to detect it. And that's why it has not yet been detected with, these large structures were not detected with Cherenkov telescopes. But if you, for example, you look in the central molecular zone, in the very dense gas in the very center, then there was detected by Hess. Okay, so that is something. I will tell you more has been done, and we believe more will be done with CTA in this regard. In terms of sources, again, Franz was saying that now we have even more than 5K. I think now we're almost at 7K sources in Fermi. At TVs, we're around 200-300. Again, this is because one, inherently sources, get much fainter. Some might have a cutoff, and then again, it is relatively hard to detect them with Cherenkov telescope, and again, telescopes, and again, CTA should do better here, increase this number by I believe at least factor of 2 or more. But anyway, all these that we see in gamma ray sky is also a great background for dark matter searches, and we have to model it and deal with it. So let's take a look a little bit more in detail. So this diffuse emission, interstellar emission that comes in the galactic plane, where does it come from? We will not go in detail. It's it's quite complex science, but basically the non-thermal sources, supernova remnants, pulsars, emit charged cosmic ray in the galactic plane. Those charged cosmic rays get trapped in the magnetic fields, they diffuse, and then impinge on the gas and scatter starlight to produce gamma rays. And the processes, as Franz was saying, the dominant processes are these three in the GeV to TeV energy band, meaning that cosmic ray protons interact with gas, with protons in a gas, basically hydrogen most likely. So these are proton-proton interactions that produce pion, and pion decays to gamma rays. Okay, so one important component here is the pion production due to proton-proton interactions. Another one is Bremsstrahlung. So electrons in the field of protons crossing the gas emit Bremsstrahlung emission, and this is another component here. And you see, both of these components, they have as target, they have the gas, hydrogen, atomic and molecular hydrogen in the galaxy. So basically, both of these emissions, charged cosmic rays, charged protons, and charged electrons hitting gas, they have the shape, the morphology of the gas maps. So this is very important when we do the modeling. Basically, we know that anything that looks like gas is basically due to these two processes. Okay? And the third process that is the hardest to model is the inverse Compton emission. So cosmic ray electrons produced by sources, they upscatter the starlight, they upscatter the low energy photons, and produce gamma rays, okay? But we do not have such a great model for starlight or for this low energy photon emission, because there is dust, there is absorption, it's very complicated production mechanisms. So while here we can say anything that looks like gas, we can subtract if you look for dark matter, here we are much, it's much harder job for us. Some more information. So this is what I already said. Like pion and Bremsstrahlung look like gas, while inverse Compton looks eerily similar to dark matter signal. These are the spectra. So pion spectra has this pion bump, which is also could be similar to some degree to dark matter emission. Inverse Compton we expect is more something like a power law. And so ideally, so now if you look for dark matter, what we need to do is to model this emission, subtract it, and then look for dark matter signals. And in order to do that, that's not easy, because in order to model all this emission in spectra and morphology, you need to solve the diffusion equation. And this diffusion equation depends on how cosmic ray sources are distributed, how is gas distributed, inverse Compton. So there is tons of things, magnetic fields, there is tons of things that enter here. We typically have these numerical solvers, GAL, Probe, Dragon, that are publicly available, that you specify all these parameters and then get these maps over there. So this works actually amazingly up to a first approximation. It's actually crazy that, one equation, even if complicated, anyway, can describe the whole diffuse emission all of the galaxy. So it works very well, but of course, not perfectly. And then when you look for dark matter, for some, residual emission, really the trick is here, how well you can do this, deal with this part. So this emission, talking about astrophysics, this is actually amazing knowledge that we learned from Fermi, because, as I was saying before, if you want to understand cosmic ray population, like how cosmic rays are distributed in the galaxy, how gas is distributed, one way to do it, you can get lots of that information by observing actually the gamma rays. So you can work back. You can say, I have my gamma ray map. I sort of know something about gamma rays. What can I learn about cosmic ray population in the galaxy? And people have played this game, and you can learn stuff. Because, as I was saying before, direct cosmic ray measurements, if you want to see what is the spectra of protons and electrons on Earth, you can measure just the spectra. But now gamma rays are giving you 3D view, 2D view. They're letting you sort of see how cosmic rays could look here or there, and so on. And so, modulo that you can solve all this, equation and have some parameters under control, you can learn a lot about cosmic rays. But then, right, why is this important for dark matter search? Indeed, it's quite important, because so this is expected signal for dark matter that we talked about last week. And you see that the galactic center region is where the dark matter signal is the highest, expected to be the highest, but it's also expected to be extended. And so basically you want to look in the middle of this mass, extended emission for something very extended. It's not easy, okay? You have some handle. This should be spherical. This is more disk-like. Spectra is somewhere different, but it's not easy search. And then on top of everything, people managed to, early on in Fermi, managed to model this emission, subtract it, and then what is left is this amazing structure of the Fermi bubbles. So this was, so this was a completely surprise discovery, because looking at other galaxies, we know that that they have radio. You know that galaxies typically have supermassive black holes in their centers. Then for some other galaxies, we know that this supermassive black hole produces huge radio lobes and things like that. But gamma ray lobes were never observed in other galaxies. So it was not actually, and also our black hole is quiescent. It's very, not so energetic now. And so nobody really thought this is what we will see. We still do not know, as Franz was saying, how exactly these bubbles were created. We know that they have very sharp edges. So this is emission in the bubbles, very sharp edge. That the spectra is very hard. You see, it's e to the -2, very flat, much harder than normal diffuse emission, which is e to the -2.7 or so. But anyway, so we do not know their origin. Might be the supermassive black hole, might be stellar activity, millions of years ago that blew up, like started winds, stellar winds that blew up all these bubbles. We're still trying to figure this out. But then again, why is this important for dark matter search? It is extremely important because if you're to look for dark matter in the galactic center, and then here in the middle, you have these bubbles. First you have diffuse emission, then you have the bubbles. It's not making our life easier. In fact, at the beginning, when people just started discovering the bubbles, when they just, discovered some residuals here, we were excited that, this might be dark matter. But then, this is obviously astrophysical emission that is causing them due to this hourglass shape. Anyway, then moving on from diffuse emission, as Franz was saying, we have all these point sources. Now, indeed, very recently, already DR3 catalog is out based on 12 years of Fermi data with around 7,000 sources. So this is amazing. Now you see all the density of sources that we have. And I'm showing here the galactic center. Okay, and you see many these are unassociated sources in the galactic center. So let me just back up to tell you more. So in general, of these 7,000 sources, what is their composition? So say more than half are extragalactic. Those are AGNs. Around 10% or so, 15, 20% are galactic, typically pulsars. And they're located along the plane or a bit above and below. But then 1/3 are unassociated. Unassociated means that we observe a gamma ray source, but then we do not yet have clear identification at other wavelength. Meaning, because Fermi has a 0.1 degree, say, at best, angular resolution, other telescopes could have arc-minute, could have tiny. So sometimes you could even have few correlations. But so how they do associations, they look in other catalogs if they find a known gamma ray emitter source in that field of view. And so for 1/3 of the sources, they do not find it. It's not maybe completely strange because some catalogs are incomplete and things and so on and so forth, but still, who knows, something weird, some new source classes could be hiding there. But among those unassociated, you see there are many, many of them, and in the galactic center region, a lot as well. Again, this is important for dark matter search because, as you've seen, we expect tons of dark matter subhalos, okay? And those subhalos are expected to shine only in gamma rays and not in other wavelengths. And so who knows, if any of these unassociated from here could have some fundamental fundamental origin. And then the third main contribution to the gamma rays, to the Fermi sky, to the GV sky, is the so-called isotropic emission. So basically, if you remove all the diffuse emission from the plane and you remove all point sources, what you're left off is not a zero. It's basically gamma ray emission that is quite isotropic, and just you can measure its spectra, okay? And so what is that from? So we expect that, for example, as you see, you have many AGNs, many extragalactic sources that are discovered above the threshold, that are too bright to be seen, above this emission. But then fainter sources that are not resolved as point sources, that emission would contribute to this isotropic emission. So basically, we expect this is the C cumulative emission from all the faint sources, extragalactic faint sources. And it did. So this is what Fermi measures. It measures it amazingly enough up to TV, like 800 GeV or so. And this is other telescopes, because this isotropic emission is observed also in much lower wavelengths. One comment here is that this can be measured basically only thanks to the fact that Fermi does not have huge cosmic ray backgrounds. Because, as you remember, these cosmic ray backgrounds are isotropic. And so the fact that you can measure this emission depends critically on the fact how much you can remove your isotropic emission from cosmic ray backgrounds. Okay? And indeed, in order to make this measurement, a completely dedicated source selection was developed. So not even the normal Fermi photons can be used for this because they still contain some cosmic ray contamination. So people doing this analysis went into the Fermi data, cleaned as much as possible all the cosmic ray backgrounds in order to make this very nice measurement. Okay, so again, so this is the measurement, and it turns out it can be explained by the contribution from all blazars, that sort of BLX contributed higher energies, and then star forming of radio galaxies at lower energies. So basically, it makes sense that it is that this one is made of contribution of all extragalactic sources that are below the threshold, as I was saying. So if you make a model of sources based on what you know from the observed ones, you can explain, the isotropic measurement by the unresolved ones. Again, together with this contribution of these faint sources, you would also expect, let me just see if I have it now, you would also expect that extragalactic emission, because you have dark matter all outside of our galaxy, and also that one should produce some cumulative emission that would also show up here. Say, some of such signals would be like this pink line here. And then you can use this measurement to either try to detect it or to constrain dark matter contribution. Okay, so moving on to the TV sky. So here, again, I'm just showing a little bit, more in detail what I said before. So if you want to find this diffuse emission with imaging Cherenkov telescopes, it's not easy. I told you basically it was measured in the reach. But there was also other progress. For example, with Hess, they performed so-called galactic plane survey, observed in detail this region. And then after subtracting sources, they measured the cumulative emission in this galactic plane, okay? So this is not like Fermi measuring really the gas, how gas shape and things like that, but it's obviously that there is some of this diffuse emission also at TV energies, just that it is hard to detect because of these limitations of the telescope. Again, the point sources, this is the map. This is the map of TV sources overlaid with 3FHL, which are the highly energetic Fermi sources. So you see that you have sources along the plane. Also, like in Fermi, you have galactic sources, you have extragalactic sources. Galactic sources are pulsar nebulae, supernova remnants in TV, and many in TV are extended. This is another difference with Fermi. Good point. So I do not have slides on that, but basically you have to sum up, basically you have to go to n-body simulations, and to sum up, so this is simulation of a galaxy, but you have to do cosmological simulation, and you sum up the signal from all halos and all subhalos. So you have to know mass function, like how many halos of each mass you have, and how many halos you have, and what is the concentration in every halo is dependent on mass. So it's a bit long formula, but it can be calculated rather easily. Right. And another interesting thing is that if you're looking, so because I see that many of you are experts, so I'm just a bit jumping, but another thing is that if you want to look for decaying dark matter, then your life becomes even easier, because for decaying dark matter, you basically have to calculate the mass of all dark matter that is outside of your galaxy as a function of redshift, and you just integrate over redshift. So in that case, you have much less uncertainties. You just know the amount of dark matter. Okay. And then talking about the TV sources, there was a very interesting development rather recently with the Hawk data, actually, where it was realized that there is a new source class. So we were talking about these unassociated sources could hide some new source classes. And in fact, recently one new source class or class of new sources was discovered with Hawk data, and they're the so-called pulsar halos, meaning that it was realized that around some pulsars, in particular Geminga and MonoGem, there is middle-age pulsars. There is an extended region. Wait, let me show this figure here. So say, again, I don't want to now be maybe too fast here, but around that, so this would be a pulsar. So the point is that pulsars after the birth, they create after supernova. Let me just now back off again and talk about astrophysics a little. So after the supernova explodes, it lives inside the neutron star, okay, which is a fastly rotating neutron star often, which is a pulsar, okay. And then those pulsars emit lots of electrons and have this beam, and this is how we detect them. But then this beam of electrons, all these electrons emitted within the supernova remnant shock shell, they often develop this so-called pulsar V nebula, which is the region around the pulsar in which you still feel this influence of the pulsar magnetic field, and where those electrons are sort of confined. And then over time, as pulsar ages and as it moves, because pulsars have kick velocities when they're created, as it moves, this pulsar V nebula slowly disintegrates. But what is a new discovery is that people realize that in a region much larger than the pulsar V nebula, there is still weird gamma ray emission, in a sense that it appears that electrons, even after they leave the pulsar V nebula, and are much farther from the pulsar, not to feel anymore the field of the magnetic fields of the pulsar or any influence of the pulsar, still remain contained in this region that is called a halo, okay? So why am I saying on this? So this is very interesting from astrophysical point of view, because as I was saying, I mean, it's a very big mystery in astrophysics how electrons produced by pulsars, how they leave the pulsar V nebula, and how they sort of the spectra of the electrons that is close to the pulsar, is it the same as the spectra that is outside, in the cosmic ray medium, in the galactic medium? And now we are seeing that the story is more complicated. There is this stage where electrons remain confined, and then somehow they seem to be released. They seem to be released in the medium. And moreover, the diffusion coefficient, like the way they diffuse within this pulsar halo, is very different from the fusion outside. Okay, so all this is very, very interesting for astroparticle physicists to understand the origin of cosmic ray electrons in the galaxy. But it's also important for dark matter search, okay? Again, so we're learning new astrophysics. As we learn it, we have to incorporate it in dark matter search, because, if you are to look for dark matter, we have to know, all the other properties of all the other sources that are out there, and how their existence might, impact our search. So, in particular, for these TV halos, we will learn, now people are studying it, we will learn a lot about what happens to electrons, but then again, these are extended sources. And we were saying the dark matter sources could often be extended, because these are subhalos, if they're closer, they're extended. And so these TV halos can then also be a background for us that we now have to take into account now that we know that they exist. Okay, so anyway, so this is more or less what we are dealing with here. So I want to say a bit just general comment about indirect search for dark matter, because as you know, you can search for dark matter in astrophysical data, or you can search in your lab, like in direct detection, things like that. So in other searches, you typically you understand your background. You have your instruments in the lab, you can understand it. In astrophysics, this is what we have to deal with, so it's harder in a sense, but it's also, to my mind, also more exciting, because you're discovering all this astrophysics as you go. So I want to say this is hard, but it's also like all the time you're finding out new stuff. So I love indirect searches for that. All right. So now assembling the cake. So what we were saying so far, we were describing what data we have. We were saying what we expect for dark matter signal, and now we talked about astrophysical backgrounds. So how do you put all this together and basically, look for your dark matter signal? And in terms of, so I will tell you just the analysis strategy over here. So there were two main approaches. There are two main approaches in the market. Some of you did already dark matter search, so you're well aware of it. So if you have, so what was traditionally used only in gamma ray, in GV range with Fermi-Lat data, is the so-called template-based likelihood fitting, or 3D likelihood. So how that works? So basically, again, you have your data, you have your background, and you have your signal expectation, okay? And then you bin your data in space. You divide it in spatial pixels, and you divide it in energy pixels, and you create Poisson likelihood function. This is a data. This is the model. So you basically deal with the counts in each energy and spatial bin. You define your likelihood that way between the model and the data, and the model itself has parameters. So the model, say, model of your Fermi data would include the template, the image, and energy spectra for your dark matter signal, okay, and of all the other astrophysical backgrounds that you have. So basically, you would make your model as a sum of all the backgrounds and the dark matter signal, and you would sort of fit it to the data by calculating this likelihood. So let me see what I wanted to say here. Right. And then so this likelihood would have, you see, this mu would have many parameters, would have parameters related to dark matter, and would have parameters related to all astrophysical components. This you do not care about. You know, you just want to find out for which parameters, for which dark matter parameters your likelihood is minimized. And then you do that based on these test statistics, okay, that compares a model, the likelihood for a model that contains dark matter with likelihood of the baseline zero model that does not contain dark matter. And you see, if this is bigger than some number, then you detected it, or you can set the limits. So it sounds a bit confusing when said, but I'm sure many of you have used likelihood already, so luckily I don't have to dwell too much about that. Yes. Yes. So the idea, so it depends. Like, I'm always confused if you have to maximize the likelihood or to minimize the minus log likelihood, right? Because you typically deal with minus log, like here, you see minus log likelihoods are what you are minimizing over, and you do it in such a way that you minimize it over all the other parameters, nuisance parameters, and you plot it, for example, as a function of your own parameter that you're interested in. Okay, and then when this gets higher than, I don't know, delta log likelihood gets bigger than 2.7, depending on your number of parameters, that's what you set the limit on your on the parameter of dark matter that you are interested in. Okay, but what is important here is that, of course, this works well if you have a good model. No, because you have, so in order to model your sky, you have to have very good models that you put it in. Because if your model is wrong, you can always define this likelihood, but you have no, you could get wrong results or underestimate your uncertainties. And then what is very important is basically that you should find a way how to incorporate so-called systematic uncertainties on what you do not know. So let me just step back again here. This might be, maybe too much to say, but I was saying here, for example, say for diffuse emission, okay? We were saying that it's very complicated to model this diffuse emission. So you can always put one model of diffuse emission and set limits on dark matter on the sky, but then or claim you found dark matter, but then if your initial model is wrong, you might reach wrong conclusions. So what you typically have to do, you have to fit many models, or at least find an analytic way how to express the uncertainties in your models before you can do the proper statistical analysis. Yes. You mean for the uncertainties or for... okay. So maybe in tutorial we will be talking. So tomorrow I have a tutorial that will be talking about fitting likelihood. Yes. So you sum here over each overall pixels. Yes, exactly, exactly. So what enters in the likelihood are the models. So how many, so in a given pixel, I is a spatial pixel, say J is an energy pixel, okay? So in each pixel, your model predicts mu counts, okay? That are, for astrophysical components, have these parameters AI, and for dark matter components, have this parameter A, which could be cross-section, like overall normalization of your signal. And then you compare it to the data, find the best parameters that fit it from the model side, and then find limits on your dark matter parameter. But we will talk more about this on Thursday as well, how it works in practice. But I mean, again, so this is what everybody does all the time. And it's very hard to actually understand additional uncertainties. So it's easy, it's easy. If I have a model, I predict counts, I fit it, I put it in my minuit or whatnot, and it gives me a number, and I'm happy. But but to estimate realistically the uncertainties you have on your model, this is really hard. And few people are, like, not doing it. I mean, yeah, admittedly, everybody puts this elephant, like under the carpet, but one should do better. One has to do better, because now more and more we have more and more precise data, and then this thing really starts to matter a lot. Okay. All right, and traditionally, on the other hand, now if you go to imaging Cherenkov telescopes, traditionally technique that is used here is the so-called on-off technique, okay? So here, the idea is, so because the biggest background, the only background that people typically take into account in Cherenkov telescopes is this cosmic ray background that is isotropic, okay? So this is because as I was saying before, no diffuse emission, no large-scale emission is detected. I mean, generally, is detected with Cherenkov telescopes, and so the only background they assume they have is the cosmic ray background. And they're saying, like, because the cosmic ray background coming to Earth is very hard to, I mean, you have a model, but then you depend on atmospheric conditions, like what really comes to your camera, this background is not so easy to model. And they're saying, we don't really actually have to model it because we can measure it. We just look and we just see only that. And so they're saying, then let's do on-off analysis, which is like this. Like, I define my own region where I have a source, okay? And this is where I put my, where I calculate the likelihood of my model. So now I'm a bit confused here. But this is where I expect my signal to be. And then instead of modeling the background, I just measure it in the off region. Okay, so I say, here I expect to have signal. This is my, here I put my model. Here, I expect that I only measure the background. So my measurement here is my background. And then in the likelihood, they sum up, how much in this on region, how much the model plus the background as measured off, well, fits the data well, okay? So they're basically subtracting from the data here, they're fitting together the emission from the off region plus your signal emission are fitted to the data in the on region. So this is smart. In a sense, this is the best you can do in principle. If the idea is let's not rely on the models, because again, here, as I was saying, the problem is if your models are not good enough, you have to quantify how bad they are. Here they're saying, let's not play this game. Let's just measure directly the background. In that case, I don't have these uncertainties in theory. But the problem here is that you see, it's very hard then to look for extended signals, because if your signal is such that it contributes almost equally in the on and the off region, then you basically measure, not measure only background in the off, you measure also the signal, the part of the signal. And so it basically fails for extended signals, okay? And that is the problem for dark matter, no? Because dark matter signals, as I said, are often extended. And so this is a bit of a problem here. But again, we just have to, know the limitations of what we do, so to interpret the results properly. Exactly. So now I will tell you more. So now with CTA, we're moving more towards this. I mean, some combination, again, is probably going to be between likelihood fitting is important, but still it's hard to model the cosmic ray background. So we're still figuring that out. It should probably be something like likelihood, but somehow calibrated by some off regions, if you can define such. Okay, so this was very briefly all about the analysis I wanted to say, and now I wanted to give some concrete examples of WIM search. First with current telescopes and then with CTA. And so this is how typically, one of the ways to present how people think about the dark matter search targets. We're talking about various targets that we have, but here they're plotted in terms of a signal strength, like where the signal is you expect it to be highest, but also the robustness, like how robust discovery would be. Meaning how high are your backgrounds? So this, how high are your backgrounds is in the other direction, no? So smaller the backgrounds, more robust the discovery would be. So, and here you have clearly the galactic center on the one angle, because in the galactic center, as you were saying, the signal is the highest, but the backgrounds are also the highest. And so any discovery would be the least robust, but you expect the discovery to happen first, okay? And then you have things in the middle, like we could look for dark star halos. We could look, as you were saying before, clusters of galaxies, other galaxies, this isotropic signal, and so on and so forth, which are, sort of signal is less, but also they're somewhat more robust. And then on this hand, you have these smoking gun regions, sort of detections that would happen, these are the targets where you do not expect any astrophysical background. So any discovery would be robust, you expect, would be really discovery of dark matter, but the signals are not so high. And this is what we discussed before. If you look for a spectral line, you do not expect astrophysics to produce spectral lines. So then if you discover spectral line, this should be dark matter signal, or in dwarf spheroidal galaxies where you do not expect any gamma ray emission, only that of dark matter. Okay, and I will start with the galactic center. As you could figure out, this is my favorite spot, but the hardest. And so, as you were probably very, very well aware, people have been performing this analysis already for 10 plus years. So since the Fermi, already from the first year after the Fermi launch, people were trying to play this game in more or less sophisticated way. So basically, this is again what I was telling you. They would take the region of interest, take the data, then build up the models, the best models that describe emission here, and subtract it to see, does this model describe well my data? And so they did this by modeling, say, diffuse emission, adding Fermi bubbles, adding all the point sources, you put everything together. With your likelihood, you define the best possible model based on these that would describe your data. You put it in, you subtract it, and then people realize that no matter what you do with this modeling, there is some residual. There is some emission that you cannot explain away no matter what you try with your models here. Okay, and so as you know, this is this funny thing that was already realized long ago, that there is such thing as galactic center excess, some emission in the galactic center that we do not yet still know the origin. And so this was very exciting. I stopped here. I think this is just up to 2014 references, but they're like in the last 10 years there is at least 5 times as many. But basically, this emission, as you know, it's quite extended. Here you can see it up to 3-4 degrees, but extends up to 10 degrees or more. It's spherical, it seems, sort of, and the spectra is something like this, again, similar to what you expect for dark matter. And again, as I was saying, like, this is this systematic uncertainty. So no matter how you change your models, like whatever you do with your models, you change it horribly, but the spectra, this is energy versus flux of this galactic center excess, seems to always be present. It changes properties a bit, but it's always there, and it's always extended. And as you know, so this would be too good to be true, because if this signal would be due to dark matter, okay, it turns out it would exactly be dark matter that you would expect, like something around with a mass of around 100 GeV, or something with a thermal cross section. So exactly what you want to find. But then this is where having astrophysical searches come to mind, because even though it seems like discovery, there is astrophysics to be understood, and one cannot make robust discoveries just based on one observation in astrophysics. So what was then very soon realized is that pulsars, which are one of the sources that Fermi started to measure, from the beginning, Fermi had like 10, 20 pulsars. Now it has 200, 300, okay? And so we now know, so this is us, this is galactic center, and so now we have around 100, 200 pulsars measured in our solar neighborhood. I mean, neighborhood like up to several parsecs away from Earth. The pulsars generally are too faint to be observed as far as the galactic center, but we know that there are many pulsars around us. And so it's natural to assume that there are also many pulsars around the galactic center, and especially that there is such thing as a bulge population of the galactic center pulsars, because you have higher star formation activity here, so probably more pulsars were produced there than general in the galactic plane. And so the idea now is that probably you have a lot of unresolved, individually unresolved pulsars in the galactic center region, and their emission is probably what we are measuring here, and not that of dark matter. I mean, it's not clear. We cannot tell with the data we have now and with analysis techniques we have now. But point is that there is this emission here. It looks awfully like dark matter. On the other hand, it could also very reasonably look like pulsars. There was a lot of discussion after that, lots of papers, lots of techniques that were trying to, fancy statistical techniques that were trying to address the question if this galactic center is more diffuse-like or more point source-like based on statistics. Because real diffuse emission would produce Poisson-like statistics and point sources, non-Poissonian like statistics, and just playing with that, people try to address the question. But the answer seemed to be that it's really hard to tell. Really, the answer depends a lot on how good you modeling your astrophysical backgrounds, and we just do not know yet. People also use very different techniques like machine learning. It seems that this galactic center excess is not really spherical, but looks a bit more like a boxy bulge and things like that. So I think at the moment the thinking is it should be pulsars, but depends whom you ask. There are people that are not convinced yet. So here I just wanted to put this note of caution, as I already said, because if you look in astrophysical sources, you are bound to find some signals, no? Because we do not know astrophysics very well. So here and there, we just, we see something weird that could probably be also described by dark matter, but often, I mean, so far always it was, either remain something weird or we realize some new astrophysics. So there are some, various discoveries of dark matter in the past 20, 30 years, and how many years they were, present. This is old. So there's Hooperon. This would be this galactic center excess dark matter. Here is 10 years. It should probably now be almost 15. Okay, so but what is the strategy? So if you find the dark matter in one target, you have to cross-check. Like you can never be sure unless you see it in the different target with different messenger and things like that. Okay, so now leaving galactic center excess and looking, so from Fermi data, basically what we have are these contours of detection, okay? If you look at higher energies with Hess, at the galactic center region, there was this very neat new analysis because Hess basically spent 500 hours, I think, 500 hours in the galactic center region, which is a lot for Cherenkov telescopes. And they also did this little survey. So they did not just observe in the galactic center, but they did this survey that covers up to 5 degrees, sort of from 0 to 5 degrees, okay? And they looked for dark matter. I mean, and they just measure the signal and then try to set limits on dark matter. So what they did this on-off analysis. So basically, they did analysis, signal region was on the galactic center, okay? This like up to 2 degrees around the galactic center, and then off region was around 3-4 degrees aside from the galactic center. Okay, and so if you play this game, you say, I measure my backgrounds in the off region, in the on region, I fit these backgrounds plus dark matter to the data, and I set limits. It seems that they got these amazingly strong limits. You see, this is thermal cross-section. This is 1 TeV. These two, I'm a bit, it's unclear to me why INASTO limits are so much better than NFW, but yeah, somewhere here would be their limits approaching the thermal cross-section. So the only thing, so these are very strong limits. The only thing to keep in mind is that because those were done with on-off technique, that means if dark matter profile would be cored, would be quite flat. It's like, when you were talking about dark matter distribution in the galactic center, you were saying it can be Caspi, but it can also be core. We just do not know. And so if dark matter distribution would be cored in a few degrees, what would happen is that you would basically subtract it in off region. And so these limits basically are vanishing if it's a core. The analysis simply does not work if you have more extended dark matter signals. So, so these are very good limits, but still they very much depend on dark matter profile. Mm-hmm. Right. Well, for Cherenkov telescopes, so exactly. So, but for Cherenkov telescopes, they assume that they are not, that they are just, it is basically just cosmic ray backgrounds. In that case, it should be the same. Right. Right. Okay. So basically, so wait, let me see. Right. So basically, anyway, so they produce these limits. I just wanted here to comment. This is the curious case of Andromeda. So as I was saying, I showed you galactic centers, sensitivity. Now moving down, I just wanted to mention this for Andromeda because Andromeda is also very interesting galaxy. As you know, Andromeda is something supposed to be just a bit bigger Milky Way. Should be very similar to Milky Way. And then Fermi discovered extended emission. So Andromeda is supposed to be few degrees on the sky, but from inner 0.4 degrees in the bulge of Andromeda, Fermi also measured extended gamma ray emission. Okay? And this is curious because it has very similar spectra to the galactic center excess. And it has also, so assuming that this galactic center excess is due to pulsars, then also this luminosity of Andromeda measurement can be explained. So basically, it's consistent, like what we see in Andromeda is consistent if the emission in galactic center excess would be due to pulsars, okay? It's also consistent if it would be dark matter, so it's not really conclusive, but the point is that we see very similar thing in Andromeda as we see in the galactic center, in our galactic center. So it's still, and uncertainties are huge. So I mean, we still have to wait and see a bit more. But still, I thought it's very nice measurement, and we will learn something very soon about this. For M31, yes, especially in CTA. No, but also here we derived. Yes, I didn't put it here, the plot. So it would be consistent. It would be you mean the detection? I don't remember. In fact, I was. You're right. I have to take a look into that, right? Because you're right. So I forgot. I mean, actually, I was co-author on this paper, so but I forgot what we did there, like in this one in 17. We focused more on pulsars, but and then we also had, yeah, good point. I'll take a look later. I don't think that we made such a nice plot. Okay. Okay. And so moving on, then looking at dwarfs. So on the other side of this game. So as you know. Yes, I'll be quick. Oh, I mean, not really as 5 minutes quick, I didn't think so. But if I could have 10 minutes, should suffice. So again, I guess you all know a lot about dwarf search, but point is that, as I was saying before, there is this population of dwarf galaxies, and one can look, and no gamma ray emission detected from them, no gamma ray emission, astrophysical gamma ray emission expected. And so, because Fermi observes the whole sky, it can just take the data from all these dwarf galaxies and feed dark matter and do the joint likelihood analysis. And this is what was done already back in the day. Here, the likelihood is fancy because the likelihood combines the fits to all, likelihood to a single dwarf incorporates the uncertainty on the J factor in that dwarf, and then you combine the likelihood from more dwarfs to make joint likelihood and set dark matter limit, assuming take into account likelihoods from all the dwarfs in your analysis. What this does is to make the analysis better than in each single individual dwarf. And so what you, so sort of these were the limits, okay, the red, the black. And you see that below sort of 100 GeV or so, you exclude thermal dark matter. So this was a huge result. Point is that even though this includes uncertainties on J factor, it does not really include all possible uncertainties. So the idea here is that sort of factors of 2 up and down could still work. Like these limits could get a bit better or worse if you add additional uncertainties. Now we have many more targets with DES, Dark Energy Survey. We have around 45 dwarf candidates. And with Vera Rubin, we'll have many, many more. And so this analysis can be and will be repeated. And is expected to increase the sensitivity. I'll show you later. Another development, it was also very interesting that all these telescopes actually came together, Fermi and Magic, Veritas, HASS, HAWK, and they all shared the data on the 20 dwarfs with these 5 gamma ray telescopes and made this joint likelihood. So this likelihood here was, summed over dwarfs and summed over telescopes, and basically made this the up-to-date, limits from dwarf targets on thermal cross-section. And you see, if you do when you do this joint likelihood, you improve. So you see, the dotted line would be Fermi alone, I guess. So here is here it doesn't improve much with Fermi's alone. But here when you start adding other telescopes that have comparable sensitivity, then you improve. The joint likelihood improves the limit above all individual limits. Okay, so summary. So in the galactic center, sort of a GeV, we have this sort of discovery, and HASS we exclude it, and then dwarfs we exclude it. I just wanted to show this, that there are many other analyses. So this is the dwarf limits, galactic center. But then if you look with Fermi data, for example, there's tons of analysis techniques, all having sort of comparable sensitivities. I don't, of course, have time to go through this. But the point is that situation is more or less like this. You have Fermi, so these are the dwarf limits. And these are the HASS limits, a bit older ones. And then basically you exclude this region, but the TV range is, TV thermal cross-section is not yet excluded. The yellow is future projection, how well we think the dwarf limits will become in the future. But basically what is allowed is from here to here at the moment. So this is what I'm showing here. Basically, there is this TV gap, the WIMP window still allowed, and more or less CTA will be the only experiment that will manage to close it. So this is what I wanted to say. So CTA is extremely important to sort of probe this remaining TV gap for thermal dark matter. So now I'm really getting cornered. But okay, so I wanted just to say that for TV dark matter, you should be careful, because in TV, it's easy to sort of model the dark matter interactions in GeV range. In TV range, you get very close to WZ bosons, and depending on the model, you could exchange many particles then in these loops, and modeling becomes a bit harder, because you would expect enhancements in the cross-section, bound states. This even unitarity limit doesn't have to hold if S wave is not the dominant annihilation channel, and so on and so forth. So on the particle physics side, the modeling also becomes more baroque as you go here. So something to keep in mind when you do this kind of analysis. Here I just wanted to show that CTA papers, CTA dark matter group works on tons of these limits already, making projections, and is preparing the ground for the first data. So there is a consortium papers on the galactic center, non-consortium dark subhalos, soon from clusters, soon from clusters will come out, and from LMC, there is from Andromeda, and then these are being written from dwarfs and spectral line within the CTA group. Very quickly, I wanted to show just that this analysis projection, how well CTA will do in the galactic center. So CTA, I said that HASS did sort of galactic center survey, but CTA will do much deeper and much larger one. And if you do this 3D like template analysis and you fit all the possible models that you expect would be there, you get that basically CTA should almost certainly sort of fill in this TV gap and probe the TV thermal cross-section. So this is very promising. Another promising thing is that you also see that even this diffuse emission that I told you it's very hard to measure at the Cherenkov telescopes, this is the predicted emission and this is the sensitivity. So CTA should even be capable of measuring this diffuse emission that I said it was so hard for Hess and other Cherenkov telescopes to do. Okay, here is something about galaxy clusters. I will not have time to say nothing about this, except that galaxy clusters are placing very good constraints on decaying dark matter. Judith will actually talk to you about tutorials, and she was the author of one of the authors of the cluster paper. And right, so I just wanted to say this, that, so as I was saying before, that CTA, right, all these analyses are ongoing. The first version, sort of, one of the versions, it's not that the work is done, because there is still space to improve the analysis, figure out things, and then also with the real data, to do the actual analysis with the real data. But we are getting ready for the first light with CTA as well in the dark matter group. Right, so here I wanted to just put some summary. Let me just even see what I was saying. That search for dark matter is not easy, but it's definitely a worthy task. The field is mature, and the astrophysics is exciting. Right, so this is right one thing. So you could look at it optimistically, that it always seems impossible until it's done, okay? And indeed, to discover Higgs, we waited 40 years. You know, for dark matter, if we wait 80, it's not, you know, it's just reasonable. But then I also love this thing, that the hardest thing is to find a black cat in a dark room, especially if there is no cat. So I don't know in which of these minima we are at the moment, but yeah, I think it's just, I mean, it's fun to do it. Yeah, here I put some literature, some maybe suggested literature if you want to find out more about dark matter, the reviews of various kinds. And I just wanted to advertise 1 minute that in our universities in Slovenia, we have this program, SMASH, that is machine learning for science and humanities. It's for postdocs, so you're young, but keep it in mind, spread the word. And so these are postdocs we will be hiring in the next 5 years, basically, yeah, 50 postdocs. And you work with us in Slovenia, but then you can spend 1/3 of your time in some other centers. We are partners with many centers, including Vitter's group here. And right, it's great conditions, lots of money from European Commission. So if you see ads for SMASH, pay attention. This is all I wanted to say. Okay, thanks.
Questions?
Okay, so when you were talking about the axis of the galactic gamma rays, so you said that it doesn't depend on the model. That
it does depend.
It does.
Yes.
Oh,
I know. So maybe I did not let you finish. So
yeah.
Tell me the question.
Like you said, like it doesn't matter the model you adopt. You always end up
that's true.
having the access.
So you're right.
So
you're right.
how correct is that? Like how if you change the model, how it changed the access?
Right, so this would be one of the things to show it. Exactly, so this is the spectra. So you see all these lines, like let's say this yellow band. So depending on so for many models, your spectra falls in this yellow band. So you see some spectra could be something like this, like very peaked around whatever, 10 GeV, or it could be something quite flat with long tail, okay? But it's always there, it's never really zero. You always have something non-zero. That was the statement. So you never have, it's never consistent fully with zero, but the spectra could be very, very different.
So the other thing was how much it impact the fact when you take the Fermi bubbles to be constant brightness. Is that that change if you don't take it constant?
So this is a very good point. This is a very good point because how do you actually, not knowing the origin of the Fermi bubbles, how do you even define Fermi bubbles? Maybe Fermi bubbles are a thing that has, you know, a little bulge here. Maybe it's just part of the explanation of the bubbles. That's true. That's a very good point. Indeed, it could be. So the point is, what is the bubbles? And because we do not know what is the bubbles, we are forced to model it with some model, meaning like, say, uniform emission, because it seems uniform up to here. No, and so we say, like, okay, let's assume it's, I mean, you know, uniform out there, but not knowing, who knows how it is exactly. Great question. No, well, you see with Planck, you see Planck haze, and Planck haze is something. So Planck haze is something that is not. I mean, it extends not really up to there, up to here. Right, it's a bit larger than galactic center excess. And it's hard electrons. So it seems that the same electron, if electrons would be explaining the bubbles, they could be consistently explaining the haze. But it doesn't have the spectra of dark matter, sort of the haze. But anyway, it's not, again, it's a messy region, right? That's why it's impossible to say this is discovery of dark matter, even though it's appealing, right? But still, it could be that this thing here is something like, you know, electrons pushed away, whatever, by winds, but then you have pulsars or something in the center. It could be completely different origin, but could be also related, right?
Okay, thank you. First, I would like to know how exactly what we have to do to put these bounds on dark matter models, because I didn't get exactly how I translate my...
From data analysis part. You mean?
Yes.
Right, exactly. From likelihood perspective, you're saying. You mean sort of this plot? I mean,
Yeah,
you mean more generally?
How do you? Yeah, exactly. Yeah, how do you connect the likelihood function and these things with the bounds on the cross section, for example?
Okay, good. So I'll say this now very shortly, but good question, because then I'll make sure that on Thursday we really, you know, explain this in more detail. Okay.
Okay, so I'll ask you some.
No, good, no, excellent, because I did not know how much this is obvious and how much it is not obvious. Indeed, it's not trivial, for sure. So just to make it, you know, just to say it now quickly, and then we'll say it, you know, more slowly or more in detail. How you do it is that you define first your baseline likelihood. You know, your model, say, without a signal, or your this would be this thing on the bottom.
It would be like background.
Right, it would be like background, like one model that is explaining your data without a signal.
Okay. So.
Right. Then you make a model that includes your signal. Okay, and then you plot, and then you calculate the ratio of the two. Okay, minus log likelihood of the ratio of the two, and you basically so this AX, which is your dark matter parameter, is what is actually sigma V here, okay?
In this case, this dark matter parameter could be, for example, the coupling of my symmetry.
Sorry, tell me again.
This dark matter parameter could be my dark matter mass, or
right, typically something that normalizes your signal, that makes it higher. Say you have your template, you're fitting your dark matter. So I did not plot it here. You fit your template that looks like a spherical emission of dark matter, and this could be a parameter that just makes higher or lower signal, just overall normalization. Say in sense sigma V. Say this is the question you want to ask: how much dark matter I can add to the data in order to exclude it. And so what you do, you artificially here you increase this sigma V from 0. You plot. You choose first cross section 0. When it's 0, then these two are the same, and the ratio is 0. The logarithm of ratio is 0. Then you increase cross section. You say you put it to 5 in some units. You put it to 5. You calculate the likelihood of normalization being 5. Minimize this for all other parameters. Find the ratio and plot how much this likelihood is here. Okay? And then you increase this AX, and you plot the value of your likelihood as you increase the X. And then you say, when my likelihood ratio worsens, then I don't know, 2.7 is typically, I don't know what these numbers, then when it worsens more than given amount, statistically meaningful amount, then that cross-section is my limit, like say 10. That would be my upper limit on the dark matter. So this is how much dark matter I can add before I statistically significantly worsen my fit, so that it's clear that my background model is not a good fit anymore.
Nice. Thank you.
Sure. It's yeah.
Further questions?
Can you go to the slide where you show the uncertainty in the J factor?
Uncertainty in the J, for the dwarf analysis. Yes. Ecco, here. This one?
That's a question because I have seen the Fermi-Lat paper, and that in the uncertainty factor in the bonus part, it's J, it's the medium of J. And I have seen already just J also. Is that, you know what's the difference between the two?
So, okay, so I guess not really, because I did not work on dwarf analysis, but the point here is that you're looking that the difference between your actual J and the mean J, you divide it by 2 sigma, by the uncertainty on J. And so if it's more than uncertainty, basically doesn't matter. But if this difference becomes much larger than uncertainty, then this becomes important factor in your likelihood. It worsens it a lot. This is the meaning. Then I don't know, maybe they rewrite it in different ways. I'm not aware. I did not really follow literature on how this was changing.
Thank you.
Right. This is just saying, like, you penalize all the J factors that are worse than 2 sigma than the mean.
Further questions? No? So let's thank the speaker again.
Thank you, guys.